Hello guys, welcome back. So we were talking about eigenvalues, eigenvectors, and eigenspaces, right? And their relationship with linear transformations, right? So, so pretty much we're talking about eigenvalues and relation with linear transformation. Okay. Eigenvalues and eigenvectors, of course. I mean, more importantly, eigenspaces, I must say. Okay, and very importantly, I mean, really, the point that we tried to stress was that other than proving a bunch of properties and also discussing the usefulness of some of these properties, such as diagonalization of matrices if your eigenvalues are sort of special. More importantly, what we really wanted to figure out was that what happens when I have like something like this, okay, or more importantly, like what is the null of t minus lambda 1 of I. Okay, and if you recall, we said that there is this relation that holds, which means I have the entire vector space as a direct sum of their one-dimensional subspaces, right? Assuming the vector space is of dimension L, right? What this implies is each one of this is a one-dimensional subspace, and each one of these just contains one eigenvalue and its corresponding eigenvector, so it cannot be injective. So this is not an injective map, right? But what you can do is, instead of looking at the entire vector space, you can look at their individual one-dimensional subspaces, and you can figure out the eigenvalues and eigenvectors, and you can have a direct relationship between the entire vector space and the corresponding subspaces. What this also implies is that a dimension of V is equal to dimension of the null of t minus lambda I plus dimension of null of t minus lambda 2I plus dot 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 dimension of t minus lambda ni null space, right? And also, if you take each one of these subspaces and take an algebraic addition, then you will recover the entire vector space. Okay, all right. And there is as we also know, there is always this relationship between a linear transformation and the matrix induced by it, right? And the matrix induced by it. And there is always a basis of the vector space. So if you have this vector space, right, a linear operator, and U is a subspace of V, then there is always a basis V1 through Vn in V, such that you can represent the m of t in terms of the basis V1 through V. Okay, and as a consequence of all the relations that we proved, I mean, we know that if I have an upper triangular matrix, if M is an upper triangular matrix, right? If M is an upper triangular matrix, right? What we wanted to know is that without computing the determinant of that upper triangular matrix, is there a way to straight away know that the eigenvalues of T consist precisely of the entries of the diagonal? Okay, all right. And I mean, it's pretty simple, right? So what about the eigenvalues? Okay, so as we know that V1 through Vn is nothing but a basis of V, right? We know that a basis of V, right, with respect to which T has an upper triangular matrix, right? I mean, because this matrix is induced by T, right? So with respect to which T has an upper triangular matrix. Okay, or T is upper triangular. Okay, then I mean, what I do is the matrix induced by T, which contains a basis vector of this, can be easily written as lambda1, lambda2, lambda n, and this is star, right? And all of these elements are 0 because this is an upper triangular matrix, right? Okay, and these lambdas are nothing but they belong to the fields, okay, right? And so therefore, I mean, if I look at M, the matrix of T minus lambda I with respect to the same basis vectors, right? This can be easily written as lambda1 minus lambda, lambda2 minus lambda, and lambda n minus lambda, right? Okay. Now, what do we know about this T? T is not invertible, right? And this is what is important, right? If you recall your earlier results, that non-invertibility of the linear map is equivalent to existence of the eigenvalues. We have seen that result multiple times, right? So T is not invertible if and only if what? If and only if this is a null, because this is a null, like this belongs to the null of T, right? So that means that these guys have to be 0, the diagonal guys have to be 0. So that means T minus lambda is not invertible if and only if lambda equals one of the lambda i's, right? So if lambda equals any of the lambda I, any I, okay, all right. And therefore, lambda and these lambdas, lambda 1s, lambda 2s, lambda n's are the eigenvalues. So therefore, lambda is an eigenvalue of T, right? If and only if lambda equals any of the entries of the upper triangular matrix, any of the diagonal entries of the upper. So these guys are what? These guys are just the diagonal entries of the upper triangular matrix, right? So therefore T is not invertible and lambda is an eigenvalue of T. So since T is not invertible is equivalent to T has an eigenvalue. We have seen this result. T has an eigenvalue, right? So we can easily conclude that T has an eigenvalue if and only if lambda is the eigenvalue is one of the diagonal. Okay. Similarly, I mean, a very simple extension of this, or rather a corollary of this, is that if you replace the upper triangular matrix with a diagonal entry, then it is further simpler because then these guys also go away. These guys are all 0, and the only non-zero entries you have are along the diagonals, right? And therefore, a basis such as this will be, perfectly able to describe this. So, in other words, if I have a diagonal matrix B, which is just like this, lambda 1, lambda 2, lambda n, because everything else is 0, then with respect to this particular basis, right, I will have the corresponding eigenvalue eigenvector equation, right? And I get this straight up. Okay. Now, I mean, unfortunately, all matrices induced by the linear transformations are not diagonal matrices, but that is something that we have to live with it. But if somehow we are able to diagonalize the matrices, then our life is simpler. Okay. All right. So, I mean, that's the only thing that was left from last time. And this concludes chapter 5. Okay. All right. Let me save this and then I'm going to move to the next chapter a little bit. Okay. Now, before that, there are a couple of things that I wanted to say, and I'll just write it onto this whiteboard itself. which is if you have seen the classroom announcement, I have posted the date for the second test, right? Test 2, which is on October 12th. Okay, it will have the same structure, MCQ. Okay, there will be 5 questions, each question having 2 marks, and therefore, I mean, it's like it will be shorter compared to the last test, and therefore the time that will be given to you will be 50 minutes. Okay, 50 minutes, and so the content is chapters 3, 5, and 6 a little bit. I mean, whatever I'm able to cover today. Okay, till the end of the class today. Okay. The way this week's lecture sequence is going to go is that today I'm going to talk about inner product spaces, which is chapter 6, right? I'll start talking about inner product spaces and inner products. Then the next class, we will talk about some very nice and interesting applications of eigenvalues in other areas of computing, except the ones that we have already talked about. We have already talked about PCA, which uses eigenvalues and eigenvectors, singular value decomposition, which also uses eigenvalues and eigenvectors, right? I mean, any other method, I don't recall if we had talked about any other applications, right? Okay, but there are some other applications on the graph theoretic side, on some other areas of computing, which are used in social networks and image processing and so on and so forth, which uses eigenvalues a lot, and some important results about eigenvalues. Okay, so that we are going to talk about Wednesday. Friday, I understand that some of you are having difficulty with the change of basis, right? So I'll go back and talk about change of basis a little bit. I'll take an example and explain how change of basis works. And the rest of the class I'll spend in refreshing the material for your test. Okay, all right. Okay. Okay. So now let's start talking about inner product. And more importantly, okay, all right. Now, this is chapter 6 of Axler. Now, when I say inner product space, now I have a question for you. When I say inner product space, what do I mean? I mean, why am I calling it inner product space? Any idea? Any idea, guys? Why am I calling it inner product space? So far we have spoken about vector spaces, right? I mean, different forms of vector spaces, subspaces, and all that, linear transformations on vector spaces, right? I mean, we have, and from that, we actually branched off to talking about eigenvalues and eigenvectors, right? So now I'm going to talk about, or I want to talk about inner product spaces, right? So what do I mean by this? I mean, why am I talking about an inner product space? Why am I not just talking about inner products or dot products. Anyone? Nobody? Okay. Well, what is an inner product? You know that, right? I mean, inner product is a dot product. But I mean, a geometric interpretation of the inner product, or if we want to think of inner products in R2, this is R2, right? Just so that we get a motivating example, right? So this is just our vectors are just coordinate representations, right? So you have a horizontal direction and a vertical direction, right? And you drop a perpendicular like an orthogonal component onto the horizontal spaces, right? And this is just a projection of this vector into this direction, and this is just a projection of the vector in this direction, right? Okay. So, but if you do that, it's actually this is your x1 and this is your x2. And from the Pythagorean theorem, we know that this is nothing but square root of x1 squared plus square root of x2 squared. Now, what is this? What is this square root of x1 squared plus x2 squared? So your vector representation is nothing but this, right? Okay, and you have this, which is nothing but the length of the vector, right? Which is nothing but the length of the vector, right? And this we conveniently call as the norm, right? This we call as the norm of the vector. We have seen elsewhere that the norm of the vector can be actually written as the inner product of dot product of the vector with itself, right? Okay. Now, also we know that if we just think of a dot product, if we let's think of Rn, which we cannot visualize, right? So that we have components in n direction, right? Then the dot product between two vectors in Rn is nothing but we can write it in a coordinate representation. If we want to write it in a coordinate representation, it's like this. So these are things you probably know from high school or first year college algebra, right? Okay.
Excuse me, sir.
Yeah, sure.
So how can we write norm of x as dot product of x and x? That should be norm square, right?
Norm of x squared, norm of x, what are you saying? It's just
So dot product of x with itself should give norm square
norm
of the norm.
squared.
Yeah.
Square of the norm, right, you're right. Yeah. Okay, thank you. So, but the dot product itself is just a vectorial representation of this, right? So your x vector is in the Rn, your x is just, you represent x in this fashion, you represent y in this fashion, right? And so you can just write this. So this is just your good old dot product, right? So when we talk about inner product, is just an extension of dot product, except for the fact that when we talk about inner products, we actually talk about inner products both on the set of real numbers as well as on the set of complex numbers. Okay. All right. So, I mean, there are some nice properties of inner products. And also we know that, I mean, because we have this kind of a representation, right? And these guys are scalars, right? x1, x2, x2, y2, y1, all of these are scalars. So these are individual components of the vector. So I can easily write it as y1, x1. And so therefore, individually, they all commute, right? Yn, xn. And so therefore, I can just write it in the following manner, right? So as a natural extension to dot product, I can say that the inner product of x and y is nothing but the inner product of yn x, or the dot product of yn x if we are in the set of real numbers. Okay, all right. Okay. So now, since we have to talk about the set of complex numbers as well, I mean, there are some. Let's recall. I mean, if we are recall from chapter 4, right? Chapter 4 and complex numbers, right? That if lambda is a plus ib, where a and b are both drawn from the set of real numbers, then the absolute value of this is given as square root of a square plus b square. You know that, right? Okay. And then we also know the complex conjugate of this is a minus I. Okay, all right. And if you take the norm of this or the magnitude of this, it is going to give you the same, right? However, what we know is that if I take the magnitude of the complex conjugate and square it up, I'm going to get this. Okay, all right. So these are useful properties of complex numbers that we will use. Okay. Now, if we are defining my vectors over, a field of complex numbers, right? Then the norm of that vector is defined in the following manner. I have to have the absolute value inside the square root because I need to ensure that the norm is positive. Because since norm is nothing but the length of a vector, right? So it cannot be negative, right? That's the reason I need to have this modulus or arguments on absolute values of these complex numbers inside the square root. Okay, all right. And similarly, if I'm just dealing with complex entities, right, then the inner product of W and Z, like two vectors, is nothing but W1 Z1 conjugate as Wn Dn complex conjugate. Okay, all right. So what is an inner product? I mean, in general, if you look at it, what is an inner product? You take the inner product of two vectors. What are you getting? What are you outputting? You're actually outputting a number, a scalar, right? So we can think of inner product on a vector space as a function that takes an ordered pair, right, of elements from the vector space and maps it to a number. Okay, and it has a bunch of properties, and it turns out that the reason why we talk about inner product space is that the inner product space satisfies all the properties of a vector space, but it's a special kind of a vector space. Okay, with some additional properties. So it's a more stronger notion of a vector space, right? Okay, not all vector spaces are inner product spaces, but an inner product space is a vector space. Okay, all right. So an inner product has a bunch of properties. And the first one is positivity, okay, which means that I take the inner product of a vector with itself, it's going to give me greater than or equal to 0 for all vector spaces, right? And then there is the second property, which is known as definiteness, right? Which says that if my inner product is 0, then the only possibility under which it can happen is that the vector itself is identically 0. Okay, and the third property is the additivity in the first component. Okay, all right, which means that if I have like this, then this is nothing but this. Okay, and the fourth property is homogeneity, which means if I have a scalar multiple like this, what I have is I can pull the scalar out and I won't have a problem. However, if I have a scalar multiple in the second component, when I pull the scalar out, it will be the complex conjugate of that scalar that will be pulled out. Okay. And the last one is called the conjugate symmetry, which means you take the inner product of V and W, and that is equal to WV conjugate. Okay. All right. Now, you must know that every real number equals its complex conjugate. Thus, if we are dealing with a real vector space, then in the last condition above, I can simply get rid of that bar above, the complex conjugate, right? We don't need to care about the bar. However, if we are dealing with complex vector spaces, we need to keep the bar. Okay. So what is an inner product space? An inner product space is simply a vector space that satisfies all of these properties with an inner product defined. Okay. All right. Right. So when I talk about real vector spaces, like sets of real numbers, this inner product space is also known as a Euclidean inner product space, or this inner product itself is also known as a Euclidean inner product. Okay. All right. Now there are other examples. There are examples of inner product spaces like something like on the set of polynomials, right? Which I'm going to. It's better to give an example here itself, right? An example of an inner product space. Because these are examples. Now, the inner product space could be finite dimensional, it could be infinite dimensional, okay, as well, right? I mean, so if I think of all polynomials with its coefficients in the set of complex numbers and degree at most n, right? So we know that such polynomials are a vector space in themselves, right? Okay, then an inner product defined on such polynomials is usually in the following manner. Inner product of U and V is defined as a, I mean, 1. Okay. All right. All right. But I mean, as I said earlier, that we are not going to worry about infinite dimensional vector spaces. But if you do, then you define your inner product spaces like this. Okay. This is one of the ways of defining inner product space. Okay. All right. Now, the first property is trivial, right? I mean, there is not much to think of or doing about the first property. The second property is also sort of trivial because it also says if you take the inner product of a vector with 0, you are going to get 0, right? If you take an inner product of 0 with itself, you are also going to get 0, right? Okay. However, the second and third properties, I think it's very easy to follow. So I'm just going to show one. Okay. All right. And then move on to the other things. Okay. Now, you have seen that the third property, which says that if I have something like this, then, I mean, how does the additivity rule takes into account? You know that with inner products defined on complex vector spaces, the conjugate symmetry property holds, which means that I just switch the components among each other, right? The first component and the second component. But if I do that, I'll have to wrap it around with its complex conjugate. Okay. And you know that complex conjugates in themselves are additive. So what this means is that I have something like this, right? Okay. Or rather, I mean, I can do it like this way, and then I will split this up, right? Which is okay. All right. And then what is this? This is nothing but, this component is nothing but from the same complex conjugate symmetry property is U inner product V, and this is nothing but U inner product and that's it. Okay. Similarly, you can show that the homogeneity property is also satisfied in the same manner. Okay. And an extension of this, I mean, when we talk about norms, right, norms of inner products, right, when you talk about norms, right, a standard way of defining the norm is nothing but you take the inner product with itself, right, and take the square root of it. Okay, all right. And similarly, when you define inner products on infinite dimensional vector spaces, as the one example that I have shown you, you just take the integral and then take its square root. Okay. And similarly, when we have something like this, then what we know is by definition, this is nothing but the inner product of itself, right? And so what you do is from the properties of the inner product, you can take the scalar out from the first component and nothing will change, right? And then what you do is when you take the second component out, it has to come out with its complex conjugate, right? Okay. But however, since you are dealing with scalars here, right, you can write it as this, and this is nothing but the norm of v square. Okay, all right. We have also seen that two vectors, if the inner product of one vector with another vector is 0, that means that u and v are orthogonal to each other. So the discussion of inner products is important in the sense that it does actually give us very useful properties and results on orthogonality, and from there we can actually come up with an elegant solution to systems of equations via least square method, okay, and other things. Okay, all right. So there are some interesting properties that, I mean, are satisfied as far as norms of inner products are concerned, and the first one of these properties is the Pythagorean identity. Is the Pythagorean identity, which is if u and v are orthogonal to each other in the vector space V, then this has to be true. Okay, and you have already seen this in a two-dimensional space. It's easy to visualize, right? Okay. So now, but how do we show that this is true? It's sort of trivial. We just use the same properties of the inner products that we discussed and we know, is that we are just talking about the norm of something, right? So this norm of something will be nothing but the inner product, right? Okay, and we know that this can be broken down into what? Because of the distribution, right? Okay, all right. Now, what do we know about u and v? We know that u and v are orthogonal to each other. So this has to be 0, and this has to be 0 as well. And so we are left with only these two quantities. And so therefore, this is norm of u square, and this is norm of v square. And so this is the Pythagorean. It just says that the length of one vector plus the length of the other vector, I mean square of the length of the first vector plus square of the length of the second vector is equal to the square of the length of the hypotenuse. That's what it says, right? So this is the Pythagorean identity, right? However, this notion of orthogonality gives us some very useful tools. And one such useful tool, which is used in a lot of other applications, is that how could you, let's say you have two vectors in a vector space, then I would like to write one as a scalar multiple of the other plus a vector orthogonal to itself. Okay, all right. So it's something like this. This is what I want to do. I'll just draw the picture and move on to the next slide. So this is something that I would like to do, right? So let's say this is my origin, right? And I have a vector v in this direction. And you know that, I mean, if you are not falling off the span of v, then, I mean, you can just have a scalar multiple of that vector v, and you were somewhere over here, right? Okay. And then you have another vector in this direction, right? And you just call it u, and just drop a perpendicular in this direction, right? So that your sort of this AV is nothing but a projection of V in the direction of V, right? Okay. So the idea is, how do I express U in terms of these two vectors? Now let's call this W, okay? Now what is W? W is nothing but U minus AV, isn't it? Right? Okay. So by the rule of the triangle inequality, what you can easily see is that if I want to express U as the sum of two vectors, which is the two sides of the triangle, this is nothing but V plus W, which is U minus A. Okay, all right. Now, this U minus AV, we should notice that this U minus AV is actually orthogonal to V also, right? Okay, correct? I mean, the way you see the visualization. So therefore, when I take the inner product of U minus AV with V, that I must get 0. Okay, all right. However, what that implies is that if I expand this out, I have the inner product of U and V minus A inner product of V and V equal to 0. Okay, all right. And therefore, I mean, because this A is nothing but a scalar, right? This A is nothing but a scalar. And I would like to know what this scalar is. So that scalar is nothing but the inner product of U and V divided by this. You have seen this trick, but when I shown you this trick in the context of solving another problem, I did not talk about inner product spaces in general, but this is a very, very standard trick, right? And so what is the objective? The objective is that you represent, I'm sorry, you should have noticed, tell me this, AV plus U minus AV, right? Okay, so the objective is that you express U in terms of this, okay? All right, so therefore, I mean, what I'm able to write, because I know U is AV plus U minus AV. So what is AV? I know what is the value of AV, right? Okay. So I can just replace that with V and plus U minus AV. And I know that once again, U minus, I mean, what is the value of AV? AV is this. Okay, so that way I'm able to write U in terms of U and V. I mean, you may ask why do I need this? I need this to show a very, very important inequality, which is actually, I mean, you probably have heard of the inequality, but may not have used it or seen it why this is true, right? And that is known as the Cauchy-Schwarz inequality. Okay. Well, you must have heard of Cauchy, right? I mean, you must have heard of Cauchy in several different contexts, right? Cauchy-Riemann equations, Cauchy-Euler equations, Cauchy's integral, Cauchy problem, Cauchy this, Cauchy that, right? Okay, all right. So the Cauchy-Schwarz inequality says this: for two vectors in V, I have this result. Okay, so this is what Cauchy-Schwarz inequality is, right? Okay. Now, this inequality will become an equality if and only if u and v are a scalar multiple of each other. Okay, all right. Now, I mean, we will of course verify this for non-trivial results. Okay, so we will consider to begin with, we will consider that v is non-zero. Okay, all right, and the orthogonal decomposition that we have seen in the last slide, the orthogonal decomposition, that you can actually write u in terms of any vector like a v plus w, right? Which is this, is that u equal to av plus w. So right, okay, where w is orthogonal to v, right? I mean, imagine that picture. This is v, this is av, this is u. We drop a perpendicular, right? Okay, so right, so and this is w, right? And so therefore, by the triangle inequality, u is equal to av plus w, and that is exactly what and we know that this is a, right? This is a, as we found out from the last slide. Okay, all right. Okay. Now, I mean, since this is orthogonal, this arm is at right angles, right? I mean, the Pythagoras theorem will hold for this triangle, correct? So by the Pythagorean identity, what we know is that this is the longest, this is the hypotenuse u, correct? So therefore, norm of u square is nothing but norm of v square plus norm of w square, right? Okay. Okay. Now, sorry, this is not norm of d, this is norm of av, right? Okay. So because the v is only up to this, av is up to that, right? So norm of av square. Now, what is norm of av square? What is a? A is this guy, correct? Okay, all right. So a is nothing but the inner product of u and v over the norm of v square and this times v, the whole thing squared plus norm of w square, right? Okay. Now, what this is that what do we know about, I mean, what can we conjecture from this equality? So let me write this norm of u square. Please know that all of these guys are greater than or equal to 0, right? I mean, the left hand entities on the left hand side and entities on the right hand side, they are greater than or equal to 0, right? So this equal to this plus this, and this is a positive quantity. And that implies what? That norm of u square will be greater than equal to this guy. Right? If I take away the w, because this all of three are positive quantities and a equal to b plus c, right? Where c is a positive quantity, so that implies from algebra that a has to be greater than or equal to b, right? Okay, that is exactly what I have done. Now, just look carefully. There is already a norm of v square inside, right? So when you pull it out, this becomes norm of v to the power 4, and this will be norm of v square. So therefore, this will be simplified to. This will be simplified to what? This will be simplified to the, we can write it in the following fashion. And this will be simplified to Okay, all right. And therefore, I mean, you can rearrange the terms, you can pull this to the other side, okay, and take the square root, and you will see that you are going to get the Cauchy-Schwarz inequality, right? Very, very simple to see. So this is norm of u square, norm of u square greater than or equal to norm of this. Take the square out, and you're going to get this. Okay, because a lot of these inequalities are helpful, because when we solve the least square problem, we actually require a lot of these identities or inequalities. Okay, all right. So the next one is the triangle inequality. Which says that I have two vectors from the vector space, then norm of u plus v is less than or equal to norm of u plus norm of v. Okay. Once again, this will be an equality only if one of u and v is a non-negative multiplier of the other. Okay. All right. Now, I mean, obviously, I am actually progressing in one particular sequence, because while proving the Cauchy-Schwarz, I required the Pythagorean, right? You will see while proving this, I will require both of the earlier results. I'll start with the square of this norm, because square of the norms are always easier to handle. Okay, so this is nothing but, as you know, this, right? And you know that this is u plus v plus uv plus vu. Okay. Now, this, the first term is norm of u square, the second term is norm of v square, and then the first term is fine. Okay. If I want to change it, if I want to switch the order of v and u, I can do so, but then what I will have to do is that I'll have to wrap a complex conjugate around it, right? Okay. Now, what I'm going to do is just think carefully that you have an inner product and you have the another inner product with its complex conjugate, right? Okay. And what does this mean? If I combine these two together, what does it mean? Any complex number, right? Any complex number z, right? Any complex number, any complex z complex, right? Which is represented in the form of a plus ib, where z plus is a minus ib. So when you take the sum of z and z plus, you actually get 2a, which is nothing but 2 real part of z. Correct? Okay. So I'll just use this. The real part of what? The inner product of u and v. Correct? Okay. Now, would you agree that the real part of the, now, this real part of z is definitely less than or equal to the absolute value or the magnitude of z, right? Okay, so when we talk about inner products of vectors, this magnitude is replaced by the norm, right? So this is definitely, I can now replace this equality sign with an inequality if I simply use the facts of complex numbers, right? And I simply look at this, the real part of the norm of U and V must be smaller than the norm, inner product of U and V itself, isn't it? Right? Are you able to follow this? Simple. It follows from the properties of complex numbers, right? Okay. Now, and take the magnitude of it, of course, I'm sorry. Okay, take the magnitude of it, right? And this is nothing but, when you look at this, you are actually looking at nothing but norm of U plus norm of V whole square. So this comes from, right? Why? Can you tell me why? I actually intentionally skipped a step. Can you tell me how can I write this? How can I write this in this manner? And the inequality will be preserved. Anyone? Just think about it, okay?
Sir, we'll use Cauchy inequality and write it as
Exactly. Correct. Excellent. Yes, yes. Because we know from Cauchy-Schwarz, that this guy is less than equal to the product of the norm of U and norm of V. Okay, all right. And once you do that, this becomes a perfect square of norm of U and norm of V whole square, right? And then now you can just get rid of the square, easily from both sides, and you will get your triangle inequality. Okay, all right. All right. The last dice, probably, I think probably what you can do is I can just leave this as an exercise, right? Just as an exercise. Do not submit this, just do it. Is the parallelogram inequality. Which means if once again you have U and V two vectors, then norm of U plus V squared plus norm of U minus V squared is nothing but 2 times norm of U squared plus norm of. Okay, all right. This should be easy enough to see. Okay, all right. Just think of the way how a parallelogram looks, and you are representing two sides of the parallelogram by the two vectors U and V, right? And so therefore one diagonal is represented by U plus V. However, the other diagonal will be represented by U minus V, obviously. Okay, so what you are pretty much saying is that the sum of the lengths of the two diagonals, sum of the squares of the length of the two diagonals is equal to 2 times the length of the sum of the square of the length of the sides itself, which is exactly what parallelogram identity is, right? However, it is much harder to prove if you simply rely on coordinate geometry to show this. It is very, very easy if I use inner products and norms. Okay, all right. Okay. Now, the reason for talking about inner products is because you have seen earlier that, we spent some time on orthonormality, right? Orthogonality and orthonormality, right? And we said at that point of time that one of the example of such orthogonal or orthonormal decomposition is the singular value decomposition, right? So a list of vectors is orthonormal if the vectors in pairs are orthogonal to each other and the length or the norm of each of the vectors is equal to 1, right? So that means that if you take any of such two orthogonal pairs, like a vector V with itself, and then you take the inner product of it, is basically 1, right? However, if you take any two different vectors and take the inner product of it, then the inner product will be 0. That's what orthonormality means, right? Okay. Then with the help of this, what I want to do is basically create an orthonormal basis in a vector space, right? So that I can decompose vectors into their orthogonal complements. All right. So this is the agenda, and the reason for doing that is that, I mean, we would want to solve some very complex problems which are otherwise difficult to solve. One of which is systems of linear equations, which actually basically represent a bunch of lines or planes in higher dimensions which do not intersect. Now, if those do not intersect, how are you ever going to find the solution? You can never find an exact solution, but you can actually come pretty close to it. Okay, so you will find an approximate solution by the method of E square, and that is done by using orthogonal projections and using some of the properties that we have learned in this class today and before as well. Okay, all right. Okay, so I think I mean I would finish the class today. I'll let you off a little early, but please remember that the content of the test, it is also updated on the classroom, right? The date and the time of the test, right? Okay, and I am giving you a 10 minutes of buffer time because I have noticed last time is that the test opened about 4 minutes late, and that is none of my fault. It is a problem with Scholar Form in Google Forms, right? So that's the reason I cut short the test in 250 minutes so that there is some buffer time that I could allocate to. Okay, all right. Okay. So it will be a 50-minute test. I mean, the way I structured this, it's a 50-minute test, right? But the test duration will be from 12 to 1 hour, so that, I mean, you have some buffer time. Okay, so that even if the test opens 3-4 minutes late, I mean, you don't suffer. Okay, all right. So the duration is 50 minutes, which means that it took me 10 minutes to solve that question set. Okay, all right. Okay, then guys, I'll see you next class. In the next class, we are going to talk about some of the applications of eigenvalues and eigenvectors from the real data. Okay.